this two element, that will become 1, that will become 8, sorry 8. Then in this matrix you can see this is 7, right, and here 0, so 7 plus 0 7. Then in this matrix 3 minus I, and this is 5 minus 3i. So that when we sum up this two complex number, that will become 8 minus 4i. Then 7 plus 0 again 7, then minus 3i plus 3i, that will become 0. Then this is minus 7 minus I, and here we have minus 2. So minus 7 minus I minus 2, that will become minus 9 minus I when we add this two element, right. 3 plus I, so that is, and here 5 plus 3i, so 8 plus 4i, right, 8 plus 4i, and then minus 2 minus 7 plus I, so minus 9 plus I, and then 18. 9 minus 6i, 9 plus 6i, so that will become 18 into 1 by 2. Now this equal to 4, 1 by 2 into this matrix, so that will become 4, 7 by 2, 4 minus 2i, 7 by 2 0, minus 9 minus I divided by 2, 4 plus 2i, minus 9 plus I divided by 2, and then 9. Okay. Now this is a plus a star divided by 2. Similarly we can find a minus a star divided by 2, and that is this one, 1 by 2 into 4i, 7 minus 2 plus 2i, minus 7 6i, 5 plus I, 2 plus 2i, minus 5 plus I, 12i. And when we divide it by 2 of this matrix, finally we get 2i, right. 7 by 2 minus 1, here 2 will be common from this element, so this 2 will be cancelled out, so minus 1 plus I, minus 7 by 2 3i, 5 plus I divided by 2 1 plus I, minus 5 plus I divided by 2, and then 6i. Now you can see this is Hermitian matrix, sorry, this is skew Hermitian matrix, and the previous matrix is Hermitian matrix. That we can easily prove. Directly if you want to check that this is Hermitian matrix, you can see the diagonal elements are all real numbers. How we find out that star of this matrix, that is the same matrix? You can see the diagonal elements are all real numbers, right. So that will become, when we write down the conjugate of the matrix and then transpose this, all diagonal elements become as it is, and then this two are 7 by 2 7 by 2, both are same. Then this is 4 minus 2i, this is 4 plus 2i, right. So this two are complex conjugate, this is minus 9 minus I divided by 2, and this is minus 9 plus I divided by 2. So these two are complex conjugate. So easily you can prove that the given matrix is a Hermitian matrix, and similarly this matrix, this is a skew Hermitian matrix. This matrix is a skew Hermitian matrix. Now we can write down the given matrix as a sum of this Hermitian and skew Hermitian matrix. How? See, this is our given matrix, 4 plus 2i, right, 7 3 minus I 0, 3i minus 2, 5 plus 3i, minus 7 plus I, 9 plus 6i. This is our original matrix, and that matrix we can express as a Hermitian, sum of the Hermitian and skew Hermitian matrix. This is Hermitian matrix, the first matrix. In this step this is Hermitian matrix, and the second matrix is a skew Hermitian matrix. So you can see 4 plus 2i, when we add this all elements, that is our original matrix, 4 plus 2i, then 7 by 2 plus 7 by 2, that will become 7, then 4 minus 2i, minus 1 plus I, that is 3 minus I. Okay, so this sum of all the elements are exactly this matrix, so that you can easily verify. So here we complete the solution of this question. We express the given matrix as a sum of Hermitian and skew Hermitian matrix. So let's see next question. Question 3a. Let V be the set of all order pairs of real numbers with the vector addition defined as x1 y1 plus x2 y2, that is equal to x1 plus x2 plus 1, y1 plus y2 plus 1. Now here just only define addition. Okay, here in this example you can see there is no scalar multiplication which is defined in the example. So just we have to prove that the first 5 exams for vector addition are satisfied. Show that the first 5, this is actually 5 exams for vector addition are satisfied, and clearly mention the 0 vector and additive inverse, that we have to mention. Now first of all just try to understand the definition of the addition. x1 y1 plus x2 y2, that is equal to x1 plus x2 plus 1. So the addition of the first coordinates of the both the element and then plus 1. Similarly addition of the second elements and then plus 1. Okay, that is our addition which is defined in the example. Now we have to prove that the vector the first 5 conditions for vector addition are satisfied. So how the first 5 condition are what? The first one is closeness, right? For any xy belongs to V, we have to prove that x plus y also belongs to V. The second condition is commutative law, that is x plus y is equal to y plus x. The third condition is associativity, that is x plus in bracket y plus z, that is equal to x plus into in bracket y plus z. And the fourth is identity. Identity element always exists, that means for any x belongs to V there exists identity element, we call it theta, such that x plus theta is equal to x. And the last one is the fifth condition for addition is inverse, that is for any x belongs to V there exists minus x belongs to V, such that x plus minus x, that is equal to identity element. So if we here we have to prove all these 5 conditions for addition. So let's see, check one by one all the conditions, is it satisfied or not. Let x is equal to x1 y1, y is equal to x2 y2 and z is equal to x3 y3, right? Now first of all for any xy belongs to V, we want to check that x plus y is also belongs to V or not. X plus y, that is equal to x1 y1 plus x2 y2, that is equal to this is our definition of addition which is given in the example, that is x1 plus x2 plus 1, y1 plus y2 plus 1. This is belongs to V. Why this is belongs to V? Because V be the set of all order pairs of real numbers. So definitely this both the coordinates are real numbers, clearly x1 x2 real numbers plus 1. So addition of the real numbers is also real number, right? Sum of the real numbers is also always real number, so belongs to V. Now so the first condition is easily satisfied. The second condition is commutative law. You have to prove that x plus y is equal to y plus x. So x plus y is equal to x1 y1 plus x2 y2. How we define the addition of these two elements? x1 plus x2 plus 1 and then y1 plus y2 plus 1. Now x1 plus x2 can be expressed as x2 plus x1, right? So x2 plus x1 plus 1 and then y2 plus y1 plus 1, y plus x, and that will be write down as y plus x. So x plus y is equal to y plus x. Now third condition is in bracket x plus y plus z, that is equal to x1 plus x2 plus 1, y1 plus y2 plus 1, right, plus x3 y3. So we want to prove that x plus in bracket x plus y plus z, that is equal to x plus in bracket y plus z, that we want to prove. And for that, see, this is our definition of x plus y and this is z, right? Now how we define addition of this two element? The first coordinate, sum of the first coordinate of both the vector and then add plus 1, right, as we define in the definition of the in the example. So this is x1 plus x2, x1 plus x2 plus 1 plus x3 and then plus 1. Similarly, y1 plus y2 plus 1 plus y3 and then plus 1. So x1 plus x2 plus x3 plus 2, y1 plus y2 plus y3 plus 2, right? Now x1 y1 plus x2 plus x3 plus 1, y2 plus y3 plus 1, and this is x plus in bracket y plus z. So in bracket x plus y plus z, that is equal to x plus in bracket y plus z. Okay. Now the fourth one is for any, now we want to find identity element. Now how we find identity element? For any x is equal to x1 y1, there exists theta. Theta is equal to minus 1 minus 1. This is our identity element. Why this is our identity element? Because for this theta, x plus theta is equal to x. You can see x plus theta is equal to x1 y1 plus minus 1 minus 1. That is equal to, by the definition of the addition, x1 minus 1 plus 1, right? We have to add first coordinate and then add plus 1. So you will get x1 minus 1 plus 1, you will get x1, and then y1 minus 1 plus 1, you will get y1. So hence theta is equal to minus 1 is an identity element of V under the addition. Now for any x is equal to x1 y1, there exists minus x is equal to minus x1 minus 2 minus y1 minus 2, such that x plus minus x is equal to x1 y1 plus minus x1 minus 2 minus y1 minus 2, and that is equal to x1 minus x1 minus 2 plus 1. So minus 1, then y1 minus y1 minus 2 plus 1, you will get minus 1. So hence we satisfied the 5 exams for addition. Okay. So this question was asking 5 marks. Let's see next question, question 3b. Find the basis for the subspace of P2 spanned by the vectors 1 plus x, x square, minus 2 plus 2x square and minus 3x. Now we know that dimension of P2 is equal to 3, right? P2 means the set of polynomial of 2 degree, set of polynomial of 2 degree, that is we denote as P2, and we know that in general dimension of Pn is equal to n plus 1. So in particular dimension of P2 is equal to 3, and for any basis of P2 contains exactly 3 vectors, right? So and we have here 4 polynomials of P2. Check that. So consider first 3 polynomial v1, v2, v3, 1 plus x, then x square, and then minus 2 plus 2x square. So the first row is 1 1 0, right? The second row is 0 0 1, and the last row is minus 2 0 2. Okay. We want to find the determinant. If determinant is non-zero, then the given set of polynomials are linearly independent, right? And because of we have exactly 3 polynomials and dimension of P2 is also 3, so we can directly say that these 3 polynomials are basis vectors, basis for the P2, right? So let's see, check that the given 3 polynomials are linearly independent or not. For that we find determinant. The first row is 1 1 0, the second row is 0 0 1, and the third row is minus 2 0 2. That is equal to 1 into you can see we find the determinant, that is quite easy, 1 into 0 minus 1 into 2 and plus 0 into 2. So see, minus 2 is equal to finally we get the value of determinant is minus 2, which is non-zero. So that means what, these 3 polynomials are linearly independent, and because of dimension of P2 is equal to 3, there is one important theorem that if dimension of V is equal to n and we have n number of linearly independent vectors of the set V, then that n number of linearly independent vectors are basis vectors. Okay, we don't need to prove that span of that vectors are the given set V. Okay, basically the definition of basis is B is a basis for a vector space V if the first condition is B is linearly independent, second condition is span of B is equal to V, right? But if we already know that dimension of the vector space and we have exactly that number of linearly independent vectors of that set, then we can directly say that the number of that vectors are exactly the basis vectors. So same situation happen here. We know that dimension of P2 is equal to 3. We have we considering 3 polynomials of P2 and we prove that 3 polynomials are linearly independent. So definitely that 3 polynomials are basis vectors, basis polynomial, right, for P2. So let's see.